Hello, I'm Robert, and fact-checking to help you if you're scared of many things. And this is about the Large Hadron Collider, and I'm getting so many people saying they're scared of it. There's nothing here to be scared of at all. So, what's happened? Well, they've upgraded it so it goes from 13 tera electron volts to 13.6 TeV. And so that's really quite a minor upgrade. And every day, thousands of particles, 10,000 a day, hit our atmosphere at an energy of 100 million TeV. So that's millions of times more energetic. And at the same time, the Large Hadron Collider, then if you look at the particles collisions of the same energy as the LHC, and that's 10,000 times a second that one of those hits the atmosphere somewhere on Earth. And these particles, they come from huge natural particle accelerators, big magnetic fields spanning whole star systems, but some of them much larger. The entire center of a galaxy might have particles spinning around in it in a similar way to Large Hadron Collider, far, far larger than anything that we can do. And then these particles hit our atmosphere, and they don't do anything. So these collisions are obviously harmless. So this is a calculation. So it works out at about the very highest ones, 100 millions of these TeVs, then they hit about 1 per square kilometre per century, and so that works out at over 10,000 per day. And then if you look at the collisions that are equivalent to the Large Hadron Collider, then in their safety review, so Large Hadron Collider, they did do a safety review. They don't just do these experiments, they look very carefully to make sure that they're safe. And so, because scientists care about people, and they care about the planet, and they care about things just like everyone else does. And the safety reviewers are independent of the experimenters who do the research, so they're not in any way affected personally in their own research by their conclusions. And they found that nature has conducted collisions equivalent to 100,000 entire Large Hadron Collider experimental programs. And with these 10,000 collisions per second, they put in slightly different language, techie language, and I just converted that to collisions per second in order to help you understand what they're talking about. And so why do they, since these things are happening so many 10,000 times a second, you might wonder why they bothered to make them happen in the laboratory. Why don't they just study them in the wild, as it were? And the reason is because they could be happening anywhere, 10,000 times a second, but anywhere in the Earth's atmosphere. The Earth's atmosphere is absolutely huge. And the chance of any of these things happening anywhere near our colliders, especially since they tend, the very high energetic ones, they hit the upper atmosphere, and then the very biggest ones, the 100 TeV, billion TeV ones, they split into a billion particles because they are so energetic that even the thin upper atmosphere is like a brick wall to it. It just stops instantly. So the reason that they want to make these collisions themselves is because they want to build these detectors. This is an example detector, and it's larger than a house. It's multi-story building type size thing, and that is just huge detectors in order to look for tiny particles, much smaller than an atom. And then they try to detect a few of these particles flying through the detector. And the things that they produce are very short-lived. So you can't even detect most of the particles they're interested in unless you're within a few meters of the collision. So there's no way that we can get one of these way up into the upper atmosphere. It's too heavy to go up there. And then even you could somehow position it up there, you'd be waiting for probably thousands, millions of years before you were lucky enough to have one of these collisions come anywhere near your big detector. So that's why they do it. Now, could we get up to the energies of the very most energetic particles? And so I looked up a speculative paper from 2019 which is looking at ways we might be able to construct future colliders with future technology. And it worked out that it would be possible using carbon nanotubes or special crystals, that it might be possible to accelerate in such a way as to increase the energy between 1 and 10 TeVs every meter. And at the highest end of that range, with a very small linear accelerator, just a straight line device, just 4 foot 6 inches long, that would reproduce the same level of energies as Large Hadron Collider, though in rather much smaller quantities, but it could still do the same collisions. These devices don't exist, it's just a theoretical idea at present. So suppose that we could somehow produce these devices, then that would be nowhere near big enough to get this 100 million TeV. And suppose you could continue to accelerate this huge energy increase all the way through carbon nanotubes. And they suggested there that you would get up to maybe 10 kilometers and get to 1,000 TeV. But suppose you want to get to 100 million TeV, you'd have to get this future technology, which doesn't exist yet, and then use to build a linear accelerator, a straight line accelerator, that goes all the way from Tokyo to London to Tokyo, and that still wouldn't be quite enough, because it's 10,000 kilometers that you would have to do. So in principle, with incredibly advanced technology, incredibly huge mega technology thing, much larger than anything we've ever built, then it maybe is possible, and you hardly like to see that in the file. And if we ever did get up to those energies, of course we'd have this safety review, but by then we'd understand physics an awful lot better if we're capable of building such a thing. So anyway, there's not much point in doing a safety review for it now because it's not possible. So that's speculative future technology. Now the circular collider, like the Large Hadron Collider, it's currently at 13.6 of tera electron volts, and it that technology in theory can be used to build something. If you have a bigger a circular collider and strong magnets, you could get to 100 TeV. You can't get beyond that because the technology it just doesn't work beyond that point. You just dissipate too much energy to be able to do it that way, according to this paper that I read. That's not my work, that's a paper that did that calculation. I've got a link to it in my video, in my longer debug. And so now people also are appearing me and saying they're scared because they believe that the CERN is not really a science organization, it's really doing occult rituals to try to, of some sort. And it turns out that this dates back to a prank video. And the history behind it is that this is the god Shiva, which is an Indian god, and it's perfectly normal religion. It's Hinduism. It's a very gentle religion. It's not something to be afraid of. Of course, it's different from Christianity, and Western scientists have been struck by the metaphors of Hinduism, and particularly of this god Shiva and the dancing form of Shiva, that the metaphors they use describe something, and they describe it as happening at the beginning of our universe, but also happening at an atomic scale, or of course they didn't know about atoms, but they mean very, very minute scale, all the time, every second, all the time happening. And so the likes of Vitsa Kappa and Carl Sagan and several scientists have been struck by this analogy and have written about it in their scientific works. So it was a thoughtful and appropriate gift from the government of India to give a statue of the dancing Shiva to the CERN Large Hadron Collider, and it is there proudly displayed outside the collider. But it's not used for rituals. It's not a temple. It's just a statue. But someone soon after it was inaugurated, and these must have been people who had access to CERN, because they must have had badges. So it was some scientists doing a prank, and then afterwards there were people saying, just don't do that, because we don't do these things, obviously, and if you're doing a prank like this, obviously it gets people wrong ideas because of all the crazy conspiracy theories that are running about CERN. So it only happened once, and it was this, and they've since then cracked down. They made very careful that people can't do this anymore. They just are much more careful about vetting and making sure that people don't do these prankster videos. And so they did a prankster video, and a whole lot of people wearing cowls, nothing even remotely resembling any kind of Indian ceremonies. It was just Westerners, pranksters. It looks like it's inspired by the Ku Klux Klan or something. I don't know what it was. People wearing long dark hoods, and then supposedly, and it looked a little bit like was some of it inspired by Mayan ceremonies or something. It was a real hodgepodge of ideas, and then the pranksters then claimed that this was occult rituals being conducted in CERN. It was just a joke. It was not based on anything at all. And so now, if we look at the upgrade, then the Large Hadron Collider has been offline for 2 years, and they've been upgrading it. And as you'll see, the energy, it's been at 13 TeVs for some years before then. Then they decided they've got to take it down they've got to maintain it from time to time, and they took this opportunity to improve it. So they slightly increased the energies from 13 to 13.6, but the really big improvement was much more, much better computers, much better memory, much better analysts. They've got lots and lots of video graphics accelerators, which let them do things in parallel. The thing is that the experiment collects far too much data. They can't save all the data that they collect, because we just don't have memory anywhere. No, even all the disks that you could get in the world, I don't think that would be enough to collect all the data that it streams out when they're doing these detectors, and they have the detectors full on collecting data. So what they have to do is to, as they collect the data, then they have these calculations that sift through the data using automatic soft, or it's weak AI. It's just like Google's image searches. It's basically searching for interesting things. So you tell the algorithms what to look for, and you say, look for the signature, it might be a Higgs. So it goes and looks for it, and then it finds the Higgs boson. And so they don't see the Higgs directly, but they see things that because the Higgs, even with a distance of 1 meter or 2 meters or whatever, just distance of a few meters, that's too far. The Higgs is already disintegrated by then into lots of little smaller particles. So they detect all the smaller particles. So that's how they found the Higgs. Nobody will ever probably, nobody's ever seen a Higgs. There's no way to stabilize it. It's just an ordinary particle. It's nothing to do with Higgs field. It's just related to the Higgs field, just like the photon is related to the electromagnetic field. And a photon is nothing like a magnet or the magnetic field, but it's got a scientific connection, deep connection. It's basically a ripple in the electromagnetic field, and the Higgs boson has a similar kind of connection to the Higgs field, and unlike the photon, which will continue forever unless it's absorbed by something, the Higgs boson immediately, it's just like a little splash if you drop a stone in a pond, it just is immediately gone. So the Higgs field is stable, is must be very stable to have lasted this long. It's very strongly metastable, if you want to be techie. But the Higgs boson, it immediately just disintegrates in a fraction of a second, and the 8 of those are produced in the atmosphere. They're produced in the atmosphere every 8 seconds. So the Large Hadron Collider did not produce the first Higgs. The Higgs is being produced in our atmosphere every 8 seconds. Because as I said, it just reproduces things that are happening in our atmosphere. And so the 10,000 of these collisions every second, and every 8 seconds, that'd be every 80,000 collisions, then one of them will produce a Higgs. And so that's happening in our atmosphere. And that happens every 8 seconds somewhere in the atmosphere. You get a Higgs boson is produced and immediately disintegrates. And so that's how they detected the Higgs. And we would have had no chance of detecting the Higgs by kind of trying to elevate these huge detectors up to the stratosphere in balloons or something. It just wouldn't work. So that's why they did it. Now, some people worry about the Large Hadron Collider opening portals. It has nothing to do with portals. Portals are, the idea of a portal comes from science fiction. Scientists do not talk about portals. There's nothing resembling a portal in general relativity. The portal is a science fiction idea of a kind of magical gate that you can kind of walk through and appear in a completely different part of the universe. It's maybe vaguely related to wormholes, but it's not even anything. It's not, and wormholes is highly theoretical, and nobody even knows if there even can be one in our universe. It seems to require negative energy, and we don't know of anything that is any source of negative energy. But a portal is not the same as a wormhole. The wormhole can't suddenly appear. If there is such a thing as a wormhole, it's connected to the inside of a black hole, and there's nothing even remotely resembling one of those anywhere near us. So there's nothing, and you can't create wormholes from mini black holes or anything. It just doesn't make sense. So this whole idea of a portal is not related. It's nothing related to, not related in any way to what Higgs is doing. It's just an idea not to what the Large Hadron Collider is doing. It's just an idea that people have seen in science fiction movies. And what the scientists are interested in, there's a big puzzle in basic science, is why gravity is so weak. So this is an example. This is a scrap heap. This is used for moving scrap around in scrap heap yards. And you turn the electromagnet, it's an electromagnet. You turn it on, all the metal gets attracted to it, you lift it up, you move it across with a crane, you then turn it off, and all the lumps of scrap metal fall into the lorry or wherever it is you want to put it. So that's a scrapyard electromagnet. And then if you think in your mind with your physicist's hat on, what on earth is going on here? Because that's just a tiny magnet and just electrical current flowing around in it compared with the vast size of the Earth. And yet there's no problem in picking vast amounts of metal and counteracting the entire pull of the entire Earth. The magnetic field is very short range. It can't pull large things, but it can't pull things a big distance away, but over a short distance, magnetism easily beats gravity. And then it tails off very quickly. So why is magnetism so much stronger than gravity? And nobody knows. That's a short answer. That this is one of the many unsolved questions of physics. So we have things we know very well, we have things we measure, we can measure the curvature of space and things to do with curvature of space, the slowing down of clocks due to general relativity. That's a prediction. You can measure these things to many decimal places. There are some things we just don't know the answer to, even after measuring everything so precisely. We don't know why gravity is weak, and why gravity isn't as strong as magnetism. Nobody knows. Nobody has a clue. Lots of theories, no way to decide between them. So with supersymmetry, that is one possible explanation, but it's just a theory. And the idea is that gravity is so weak because the gravitational force in some way leaks into extra tiny dimensions that we can't see. And these extra dimensions, they are not man-made, because gravity has always been weak. So it's not like the Large Hadron Collider will suddenly make gravity weak over the entire universe, and so by creating these extra dimensions. That's an absurd idea. No, what they're trying to do is to look at why gravity is already weak. And to do that, they want to see, they're looking for tiny extra dimensions, and it's kind of curled around. Now, to understand what it means by curled around, imagine you could go out of the door of this room this way, and you find yourself coming in that way from behind. That's what it means by curled up dimension. But now, imagine this curl up is so small that you can only move much less than the diameter of an atom in that direction. You merely come in from behind. And that is what they're looking for here, supersymmetry. And so we never spot it normally, because even though you might move in that extra dimension, or all the atoms in your body might be moving in these extra dimensions, but they don't go anywhere because the dimensions are so small. So that is what they are looking for. And as you can see, this idea has absolutely nothing to do with the science fiction idea of portals. It will not get you anywhere else. You just get back to where you started. And the portal is supposed to go to somewhere else, not curl you back around immediately to where you were before you've even managed to travel far less than the distance of an atom. So it's nothing at all to do with this idea of a portal. No connection. So now the main thing to remember in all of this, and there's some things I haven't mentioned, like the idea of making mini black holes, I will just quickly go over that. So this is the idea that in some theories, at these energies, it just might be possible for these two protons hitting each other, or some other collision, to create a tiny black hole, a miniature black hole. And just in some theories, in other theories it's impossible. You need far more energy. But if you get enough energy quickly enough to a small enough space, it might be able to form a black hole, with just some theories. And then if that is possible, that's a mini black hole, at microscopic, less than atom-sized black hole. So what happens to a black hole that small? Well, the usual theory is that it immediately explodes. Just like the Higgs boson, it can't last even a fraction of a second. So they would be looking for the relics of the explosion of a miniature black hole. They wouldn't expect to find the black hole itself. They would just see where it's exploded. Exploded in a tiny explosion, just like the Higgs field, because it's only atomic-sized energy. It's not got lots of energy at that point. Well, it's got all the energy of these, but it's not like a big amount of energy, just tiny amount of energy. And so but it's very concentrated. And being so concentrated, according to some theories, might cause a tiny black hole. Now, according to some theories, but this is extremely unlikely, those tiny black holes might be stable. Well, if such tiny black holes are stable, then that means that 10,000 times a second, or it might be less often, maybe it's every 80,000 collisions, like with the Higgs boson. And remember that we've had 100,000 of these Large Hadron Collider experiments since the Earth formed. So even if it's maybe it's even every few 10,000 collisions, or 100,000 collisions or whatever, it doesn't matter. It means it's like, for instance, if it happens every 100,000 collisions, that's every 10 seconds. If it happens every million collisions, that's every 1,000 seconds, and so on. So in the Earth's entire atmosphere. So if they can reproduce it here in Large Hadron Collider, then it's happening somewhere in the atmosphere, probably every day, or if it's a very rare one, several times a year or whatever. So probably several times a day, given the vast number of collisions. So whatever happens, if it does make a stable miniature black hole, it has to be safe. So how can a miniature black hole be safe? Well, it would be travelling immensely fast, and it would, a tiny black hole, if it is stable, would not be able to be very, very difficult for anything else to fall into it, because it's so tiny. And if it's stable, if it's not doing anything, then it would just fly through the Earth and go off and probably not even pick up one atom, because it's so tiny. So there is a way that it could be producing lots and lots of tiny black holes. If that is true, then the tiny black holes going everywhere through the sun, through the planets, through Earth, and it's just harmlessly and heading off and nothing happens to anything. But that is a very way out theory, and most people believe that black holes disintegrate. And this is because of the information paradox, and because of Stephen Hawking's theory of Hawking radiation and the ideas. I don't know this. This is not something I've studied. I just know the layperson's view like anyone else. I'm just summarising it as a fact checker. So but most people believe that, most scientists think that it's most likely that if black holes, if you could ever make a very tiny black hole, they would immediately disintegrate. Indeed, much larger than that. Even if you would have a large one, you know, the size of a mountain or something into a black hole, that would immediately disintegrate too. It wouldn't last very long at all, because it would radiate the energy away so fast at that size. But then, if you had something, say, the size of the moon, then something the size of the moon would be radiating energy, but it's radiating energy, the same mass as the moon, not the size of the moon, something the same mass as the moon, but it would be absorbing so much energy from just matter around it, it would actually be growing. And but actually, probably the smallest black holes are star-sized, and those are growing. They can't shrink, because our universe has just not got cold enough for them. They gain, even from the background radiation from the Big Bang, then a star-sized black hole absorbs far more energy than it radiates away. So anyway, so that's the idea of a mini black hole, but it just doesn't matter what they scare you with, what gobbledygook, what crazy ideas they come up with. It doesn't matter. Just remember that this is happening 10,000 times every second, every day, all day of your life. So it just has to be harmless. The safety review went through lots of detailed physics of different ideas, but this was basically the ground rock thing behind it all. They did actually go into lots of other detailed ideas of things that could happen, or ideas of physics and so on. But the basic ground rock of it all is that it's happening anyway in the atmosphere, and so whatever this produces has to be safe. So that's the main thing, main takeaway message. So I hope this video will help some of you to be a bit less scared, and I'll upload this to my YouTube channel and hope this will help.